Welcome to the second lecture of the fifth week. And just the previous lecture I was talking about force excitation, which was frequency independent, and now I'm continuing with force excitation, and now we are talking about frequency dependent excitation. And we will see that a lot of what we derived last lecture we can easily use for the frequency dependent excitation. We have already learned about frequency dependent excitation, especially for instance if we have unbalanced mass excitation. That's what we might have. And in this case, we are not so much talking about direct mass excitation from the wheel, but we could also imagine this to be some unbalanced mass from the engine, for instance. Then you also know that in general we can display the amplitude as u times r times omega square. If we're talking about a wheel, then of course the velocity comes into play. But anyway, important thing is that omega to the square is to be found in the excitation amplitude. And that also means that there is a parabolic relationship between the amplitude of the force and the velocity. We've seen that when we were discussing single degree of freedom systems with unbalanced mass excitation already. So that is not new. And if we are now looking at the equations of motion, then obviously we can directly come back to the equations from lecture 5.1. And the only thing that we have to consider that somewhere the excitation force that we see on the right-hand side of our first and second equation will somehow be dependent on the square of the angular velocity omega. That's what you see here. In general, we are talking again about harmonic force excitation. So we're talking about the cosine term with omega t expressing this cosine function, and the amplitude of the force is proportional to omega square, and this could be the unbalanced mass times the radius. Okay, now we are obviously expecting again, and that's what we will have, an inhomogeneous differential equation system of second order, and you see the frequency dependent amplitude on the excitation vector, which we can call again h. And of course, what we can also do is we can find again the general solution as the addition of the homogeneous solution and the particular solution. And again, as the previous lecture, we know that the homogeneous solution was already discussed in lecture 4.1. We have talked about the particular solution in lecture 5.1, and we will find today that we will come up with a very similar solution. Okay, so we can again formulate the vector h star. So we are directly sort of jumping from the real notation of the right-hand side of the equation, of the inhomogeneous equation, to the complex formulation. And in order to keep our equations fit for future systems, we are also considering, even though it is not yet the case for this model, an imaginary part in the complex excitation vector h star. Then we can directly apply the formula that connects h star with x star, and we already know that the matrix involved in this equation is the frequency response matrix, and we also know that we can formulate h star again through this equation, as we have seen here in the very beginning of this slide. Okay, so this is what we find, and obviously from this equation we can directly determine the real part and the imaginary part that we are interested in order to find the cosine related part and the sine related part, so that's easy to do. And from there we use the same formulas as in lecture 5.1 for X roof and phi roof. Nothing new about that. Okay, and now we can directly discuss the frequency response diagram, which we have calculated according to a very similar Matlab program that I explained in the previous lecture, in lecture 5.1. In red, again, we see the frequency response for the vertical motion expressed through the amplitude X roof, and we see the red line that shows us the amplitude phi roof. And typically, as we have already seen when we were discussing frequency-dependent excitation for single degree of freedom, we start with 0 amplitude for 0 excitation frequency, and going towards higher excitation frequencies, we end up with a finite non-zero value. Of course, since we are talking about a 2 degree of freedom system compared to a 1 degree of freedom system, it's not so easy to decide on a sensible scaling factor. That's why usually we do not do any scaling on the frequency response diagram when we are talking about 2 degree of freedom system or in general multi-degree of freedom systems. Of course, we can also have a look at the time behavior of this system. So we can look it up in a video here. If you compare the data that we used here as system parameters and so on, initial conditions, they are very much the same as when we discussed frequency-independent excitation, and the motion is slightly different. But again, we also see that in the end, for times larger than, let's say, 3 seconds, we have a uniform, more or less uniform appearance of the time-wise behavior. But I should also mention that in general, the behavior of a system that is harmonically excitated and which is based on a linear differential equation, this time-wise behavior is not so much of interest because much more information, as you have seen, can be deduced from the frequency response diagrams. Enjoy machine dynamics with MathWorks.